Information theory 2. And for those of you who are lucky enough to be here live during the initial setup, you found, you know how today is a day unlike some of the other days that we've had together. Here we are. Today what we're going to be talking about is parallel channels. Well, we're going to finish our discussion of parallel channels. Last time we talked mostly about optimization, but we motivated, the reason for talking about optimization is so that we have a deep understanding for the solution for the parallel channel problem, which we introduced last time, but we didn't solve. And then we'll talk about, well, what if the noise is colored? We'll talk about feedback. And this is still in the Gaussian channel case. So these are just variants of the Gaussian channel that we analyzed at the beginning of the class. And then lastly, if we have time, which I think we will, we'll address matrix inequalities, which will be useful for two reasons. One, because it will help us to put a bound on the relationship between the capacity of the Gaussian channel with and without feedback. And we'll be surprised by how little utility that is, at least in the Gaussian channel case, in terms of increasing the capacity. But then secondly, and what might be more interesting to you guys and everybody, is how one can utilize Gaussian entropy in its form to derive a lot of interesting inequalities with regard to matrices, just from information theory concepts by knowing the idea of entropy. That's kind of useful. So then Thursday, which is on the 15th? Today's the 13th, right? So the 15th, we're going to start a discussion, possibly finishing up matrix inequalities, but we're going to start our discussion of rate distortion theory, which is a really important topic. And then next Monday, a week from today, is a holiday. So there won't be any class. Okay, so with regard to reading, I think most of today's material is still in Chapter 9. But you should start reading, especially for Thursday, Chapter 10, which is the rate distortion theory chapter. And in Chapter 17, there are a couple of sections in Chapter 17 on matrix inequalities. So that's your reading assignment. And as always, I'm not sure if you can see it from here, but anything that's new, any new reading assignment, on the reading page is in red, so that you know that you've never seen it before. So there's no homework yet, and you can thank the combination of me being sick, our losing our babysitter, and my wife being away for that. So I didn't have a chance to put together a homework assignment. Another thing you can thank on those circumstances is that there's no office hours today, because I actually have to go and be a soccer dad. So whatever that is. But on the other hand, like I always say, and I know that people are really taking advantage of these offers, but feel free to email me if you want to Skype or Google Hangout for sort of a one-up office hour. If you don't want to come by office hours, you can say, hey, can I meet you on Wednesday at 10 p.m., and I'm happy to do that. If you guys want to talk then. Now, on the other hand, if you said Wednesday at 6 a.m., I probably wouldn't agree to that, so I'm not that flexible. So I apologize. Okay, so the parallel channel case was motivated by the following, by saying, well, okay, we've got a bunch of these Gaussian channels. We have this one and so on and so forth, and this one. And the idea is that there's a joint constraint on the power. So obviously, if there's no constraint on anything, it's just a bunch of independent Gaussian channels. And we're not saying that there's anything dependent about the noise sources. So the noise can be seen as a diagonal covariance Gaussian. So the only connection between these channels is that that when we code for them, we have a power constraint of this form where that the sum of the powers can't exceed some constant p. So in case this is not clear, again, the pi's are the thing we're going to try to solve for. P, without the subscript, is given. That's part of the constraint. But what we want to do is we want to allocate the different powers to the different channels in such a way that the joint capacity of all of the channels is as great as possible, is as big as possible. Or I should say the joint rates. The capacity is fixed, right? You want to set the rates and find out what that capacity is. Is there capacity? And this is sort of the whole idea of Shannon's theorem, is that, okay, well, there are these critical points. And this is kind of an interesting, I think this is a really important example, because this is the first time you've seen the idea of there being, in some sense, multiple rates as opposed to one rate. Before we said there's this thing called, you have one channel, and you send this thing over this channel, and there's this thing called the capacity, which you can't exceed if you want to have vanishingly small probability of error. Now, in some sense, we really have like these k rates, one for each channel. So we have parallel Gaussian channels, but this joint constraint. And so this really gets, or I should say, this approaches the idea of network information theory, which is that now you've got lots and lots and lots of potential rates, and you can't increase one without decreasing the other. There's sometimes a very complicated relationship between these rates, and you're trying to find regions within this, in this case, k-dimensional space that are achievable, meaning that there exists a code such that the probability of error goes to 0 if the block length goes to infinity. And sometimes these things are possible to characterize, and sometimes they're very, very difficult to characterize. And network information theory is, in some sense, looking for either special cases or very general cases of these kinds of problems. So in some sense, you could even say that this is like a very, very sort of babyish network information theory problem. Although we're going to see that it gets a lot more elaborate when we get to the end of the class. So we only have one constraint, which is this guy, 21, 22. So does everybody get the idea?
Which of the two things we're doing? Are we doing the simultaneous or the one at a time?
What we're doing, well, we're doing simultaneous with the constraint. So let me just make this clear. So this sentence here, this corresponds, that sentence was meant to sort of explain the capacity for the case that there is no joint constraint. So in this green sentence, the thing I just highlighted, it's saying, okay, well, suppose there's no constraint, we just have a bunch of parallel channels, the capacity is going to depend on the usage pattern. So do we get to sort of use them all, these channels, at the same time? Or do we get to use them one at a time? In other words, is this kind of like, using them one at a time really means like we sort of increase the alphabet size effectively. Right? So like remember the BSC where we sort of, I think it was even a final exam problem last quarter, where we sort of concatenated the graphs together of the BSC, and we said, okay, well, now rather than a binary alphabet, you can actually have this alphabet of all these different things. How does that increase the capacity? And we saw, I mean, if you got the solution right on it, we saw that the capacity has this kind of form. On the other hand, I mean, if you're just saying, okay, well, you can use them all independently, you can put some bits on this one, some bits on this one, some bits on this one, then the capacity's sum. Right? Because these guys really are just like separate pipes. The difference between having separate pipes and using the pipes together to come up with a joint alphabet. And in this case, the joint alphabet is really the vector of real numbers that you've got. Each with its own power constraint. But here, the different thing about this problem is this: is that now the noises aren't independent. The noises aren't dependent. The diagonal covariance matrix. I should write this here. Diagonal covariance matrix, but it's the powers that are constrained, and we want to find. And we know that the powers are related to the rate, right? So these are the signal powers. So obviously, if we can increase one of the signal powers without bound, then the rate goes to infinity, right? Because the capacity is infinity in that case. Yep.
The second term in that equation at the bottom is that sum of expected value of xj squared. You're
Yeah.
just pushing the expected value.
Yeah, that's right. It's a squared guy. Let me fix that. Thank you.
So So the way you allocate the power to each of the channels is the same in the case that you're using them all simultaneously and one at a time.
That's right. Well, simultaneously, yeah. Or I should say, sorry, one at a time. Yeah, right. We're using them one at a time. We're not. It's not like we can use them all the time, but it's kind of like the opposite strategy. But let's solve this, okay? Let's see what happens. Okay, so here's the capacity. Well, here's sort of the optimization problem. So we have a vector x and a vector y, and we want to find the joint distribution over x, which we're not necessarily saying is independent. Right? So it's a joint distribution subject to this constraint here. Let's zoom in a little bit on this. Subject to this constraint here. Okay. So again, that just basically says, other than that, we're not saying that the noises are dependent. So even if this constraint wasn't there, everything would sort of turn into a sum. The mutual informations would turn into sum since everything's independent. We get back to a bunch of independent problems. So this is the thing. The constraint is the thing that ties the different channels together. So then what we did is we bound the mutual information. Just the mutual information itself can still be bound. We did this last time, based on these individual channel capacities, where each channel has the capacity, again, related to the signal-to-noise ratio with respect to that particular channel. The signal power divided by the noise power in the ith channel. Subject to, well, this is just definitional. What is the power? And then this is our constraint. We're saying it's equal to an equal because imagine it was less than that. You can sort of intuitively think from this particular thing that the capacity is going to be monotonic. And if there's one, if we were strictly less than the power, it's not going to be, the capacity is not going to decrease by boosting one of them up. So without loss of generality, we can do that. So then we got this optimization problem, which is a concave maximization problem. You maximize over the vector p1 through pn of this concave function subject to our constraint. And it's a one equality constraint. It's just, this is in some sense, it's a very simple one. And then we turn it into a Lagrangian. But then the question is, why can we solve this? And so what we did last time is we spent quite a bit of time on looking at this style of problem where we want to minimize a function subject to a set of inequality constraints and a set of equality constraints. Did everybody who wasn't here see this lecture on YouTube? Good, because we're going to assume that you've seen this. And so it has a Lagrangian form here in a dual. And just to remind everybody, this is one of the critical equations about why weak duality holds, where it says that for any x prime, lambda prime, and nu prime, on the one hand, looking at the right-hand side of this inequality, if we look at the Lagrangian starting at x prime, let's zoom in a little bit. This is still this age-old problem where if I zoom in, it gets truncated on the screen but not on the iPad. But anyway, so if we look on the right-hand side, starting here, the Lagrangian at x prime, lambda prime, and nu prime, we're just taking the soup over lambda and nu, and of course we're going to get bigger. We're not going to get any smaller. And on the left-hand side, which is all this stuff, if we take the inf over x, we're of course not going to get any bigger. And that happens to be the definition of the dual function. So if we take the soup over this side, the soup over lambda and nu over on this side, and the inf over x on this side, which is exactly what this is, we get weak duality. But then on the right-hand side, the inf of the soup is equal to the optimum of our solution. And again, the reason why is because we're taking the inf over x, but any x whose constraints are not satisfied are such that this soup is going to be able to achieve infinity, and so this outer inf is never going to choose that x. And so therefore, any x that inf chooses is going to be feasible, and then you're taking the minimum over them, and that's going to be the optimum. And then the weak duality says, well, the sup of the inf, and that's the dual optimal solution. The dual function is just this thing. Yeah. It's the dual function. Excuse me. And then weak duality is basically saying that there's a duality gap. And this is somebody in this building who's trying to connect to our display, and they want all of us to together. You know, it would be funny. I should sort of let this happen, and I will post the video on YouTube. That means that their screen will be on YouTube for the rest of eternity. So maybe they'll have a letter from their girlfriend or something that says, "Sorry, I don't want to be with you anymore," and then that will be on YouTube for the rest of eternity. It's probably some undergraduate. And as you all know, undergraduates regularly get letters from their girlfriends saying, "Sorry, I don't want to be with you anymore." Okay, so strong duality means that there's no duality gap. And we talked all about this last time, so I don't want to spend too much more time on it, because the critical thing we need is the KKT conditions, which basically gives us necessary conditions for optimality. So when do KKT hold? Well, strong duality on the one hand, differentiability of all of the functions on the other hand. So strong duality, KKT doesn't always hold. But if everything's differentiable and strong duality holds, we can say, okay, well, if we're at the optimal, this must be true. We must have all these guys true, this, and this. And that's Lagrange multipliers, basically. It just basically means strong duality and differentiability. And so, like I said last time, if this is true, you can sometimes just find the solution by saying, okay, what must be true of the solution? Plug these in, do a little bit of algebra, and then the solution will pop up, especially if the problem's convex. So if the problem's convex, you get a unique solution, and this is enough. It's not only a necessary condition for optimality, but this plus algebra is a sufficient condition for optimality. But in general, these are the necessary conditions. But you guys all took convex optimization, so this is boring, right? This is all, you know all this stuff. Marianne told you all this stuff. So you don't need to know this from me. But then let's look at our problem. So our problem is the parallel channel problem. Since we're in information theory, we are a user of optimization theory. We're not a supplier of optimization theory. And we have this problem. This is a concave maximization problem with a Lagrangian. We are optimizing it over X, which is the spectra of power values. We have noises. I'm using Ni, and sigma squared is the same value. I mean, it doesn't, just a renaming. To make it convex, we just turn it into a convex minimization by taking the minimum of the concave function. There's nothing that said it had to be positive or negative or anything. It doesn't matter. We do have a bunch of other constraints that I don't think I mentioned, which is that the powers, of course, can't be negative. But that's easy. Those are inequality constraints. We can handle them with Lagrange multipliers in the formulation that we have. And we have this one inequality constraint. And as I also said last time, we could easily also put individual constraints on the powers. So like if we wanted each power to not exceed some individual channel power, that would turn this sort of triangle thing into this sort of polytope thing. So that's easy to do, but we're not doing that here. The problem is convex, and I mean it's easy to show that one of the conditions, Slater's condition for strong duality, is that there's a strictly feasible point. This is something I talked about last time. So therefore strong duality holds, everything's differentiable, KKT conditions hold. And here's our Lagrangian. So we have the objective. So now we're actually going to solve it. And so this is now we're going to use we're going to use the necessary conditions for optimality plus a little bit of algebraic manipulation to come up with the famous water filling scenario, the water filling picture. It's going to be a picture in this class, but it's something having to do with filling water. You might think, well, what does that have to do with information theory? But you'll see in a minute. So we have the objective, We have a set of Lagrange multipliers associated with a non-negative power constraint, so each of the pi's must be greater than 0 or equal to 0, and then also the joint power constraint. So this is the thing that ties all of the problems together. So it's that third term with nu that makes it necessary for all these things to happen. So when we plug in, okay, so what are the necessary conditions for optimality? Okay, so when we're at the optimal values, so pi's are p stars, those are the optimal values. Lambda i's are lambda I stars, those are the optimal Lagrangian multipliers, and nu I stars. Well, we must, of course, satisfy the constraints. They're there. These are the dual constraints here. These are these multiplicative, and I can see I've got a color. Lambda I pi is equal to star is equal to 0. These are these KKT constraints that we talked about last time. And then lastly, the derivative of the Lagrangian at the primal and dual optimal values have to be equal to 0. And I've just conveniently solved that derivative for you. And so we get this. So this is what we've got to work with. And we somehow have to take this and come up with a solution. So let's take equation 21.3. All we're going to do, first of all, is just multiply this n in. And we're going to get this. So we just multiplied the n. We get this guy. Okay. And then we can just combine two of the constraints that on the one hand, we have that lambda I star has to be greater than or equal to 0. That's a constraint. But then we can solve for lambda I star in the other thing, and we have this. And so we can then use, for example, things like this whole thing has to also be greater than or equal to 0. So that just gives us another little bit of stuff we can use. And then we can eliminate lambda I star to get these conditions in the following form. So we've got the non-negativity of the powers and this constraint. But here, now this is basically saying, remember, lambda I star times p have to be equal to 0. So here's lambda I star, because we got this from this part here, times p is equal to 0. Okay. And then the other thing we have is from this whole thing being greater than or equal to 0, we have that nu star is greater than or equal to 1 over ni plus pi star. That just comes from this stuff here. So these are the sort of slightly better form of the constraints that we've got. So there's two cases. So if nu star has got to be greater than or equal to 1 over ni plus pi star, if it was the case that nu star was less than 1 over ni, then in order for this condition to be true, then that dictates that, well, therefore that means that the power I must be greater than 0. It means that we're using some power in that channel. Okay? And when that's true, again, when nu star is greater than 1 over ni plus pi star, then we're using this condition. Since power I, since that means that this guy here, since he's greater than 0, it must mean that this quantity here, this quantity here is equal to 0. And when that quantity is equal to 0, that means that nu is equal to, it gives you an equality for nu. Nu, which is Lagrange multiplier to the optimal solution, is equal to 1 over ni plus pi star. So again, that's when nu is greater than 1 over ni plus pi star, it's got to be equal to ni plus pi star. And so we can get a relationship between the power and we can get an expression for the power in terms of nu and ni. So once we've solved for nu, we've got the power, because the only thing that's left is the noise. Now the second case is, what if nu, so here we said, in the old condition, we said, well, nu is less than 1 over ni. The other possibility is when nu is greater than 1 over ni. Now, if nu is greater than or equal to 1 over ni, then that means that the power I has to be equal to 0. Now, why is that? Well, because suppose, on the contrary, that the power I was strictly greater than 0. Okay, so that was strictly greater than 0. Then this is going to be greater than 0. And then this is going to be greater than 0 because when nu is greater than or equal to 1 over ni, and the power I is greater than 0, this whole thing is going to be greater than 0. And then multiplying them together is going to be also greater than 0, but that violates this requirement. Okay? Thus, the power I has to be equal to 0 when this is true. Okay, so 2 conditions. When it's less than 1 over ni, when it's greater than or equal to 1 over ni. When it's less than 1 over ni, you've got this expression for the power here. When it's greater than or equal to 1 over ni, the power is equal to 0. We can combine these two together into this thing here, which we can write very conveniently as the max of 0, comma, 1 over nu star minus ni. Everybody kind of following? I mean, this is algebra, really. I mean, this isn't really so interesting. But what's interesting, maybe, is that the convex optimization people have adopted this example as one of the classic examples of duality. So, I mean, even though this comes from information theory, this is a very important example, application. So with this last constraint, we essentially get the following, that the sum of the powers, this is if you're not familiar with this notation, by the way, this is a plus is equal to max of 0 comma a, so it's like the positive part of a. It's negative, you just say it's just truncated at 0. So the sum of these powers has to equal p. And this then gives us right away the famous water filling. So why is this called water filling? Because it's saying that this is a fantastic, beautiful picture. So let's fill in these. So the noises. Let's fill in the noises with I don't know, tan or something. So these are the noise. These are the noises, right? You can think of the noises as essentially being sort of hard, solid blocks. And it's raining uniformly on top of these blocks. And so what's happening is the water is filling up. Let's do the water in blue. Okay. So that makes sense, right? So we're filling up, maybe as the water's filling up, we'd first fill up, this guy would fill up first, because all the water would drain into the deepest pit. But then it would start filling up here, and then it would start filling up here. Right. And then at some point, the sum of this area, the sum of the blue region, would equal to p, and we'd stop. So you can think of it as gradually increasing 1 over nu star. So 1 over nu star is kind of like this level. This is supposed to be shown here. You can't really read it very well. 1 over nu star. That's this value here. So you're gradually increasing 1 over nu star, and as you're increasing 1 over nu star, it's kind of like corresponding to the water level. According to this uniform rain, first you fill up the deepest pit, and then as soon as you get to the top of one of the next blocks, then the pit widens a little bit, and the pits can span. It's not necessarily successive. And so here's another example where the water is shown as cyan or something. They're not necessarily adjacent. So, like for example, you'd fill up maybe this one first, and this one, and this one, and this one. It's uniform rain over the entire region. And you keep doing that until this area, this shaded area, in this particular case, the shaded area in cyan is equal to the P. And then that's why it's called the water filling argument. That's how you get the power. Now it's interesting that, if 1 over nu star is less than any of the noises, those channels don't turn on at all. You just don't use them. It's only, in some sense, through this interaction with these other channels does one know when you actually get to use a channel. Like this channel here, in this case, is not being used at all. But if the overall power constraint was bigger than that, eventually you would turn on if the water would eventually fill above it. So it's like this sudden switch when the channel turns on. It's not like you might think the solution would be something where, well, maybe the power would be proportional to the noise, or maybe all channels would be used. But this is also, this is a sparse solution. This is very similar to what people are interested in a lot of problems today with regard to things like compressed sensing and compressed sampling and sparse solutions in machine learning and all these other problems. This is an example of a sparse solution because it's saying, well, the solution to the power constraint is sparse. There are many instances where the powers are zero, namely those for which the power, or nu in this particular case, is less than the noise of that particular channel. You just don't use them. They're too noisy. But eventually, if the power constraint is relaxed enough, you'll even use some of the noisiest of channels. Okay, so that's the famous water filling picture. Any questions about this? Oh wait, let me just, before I open it for questions, give you the final capacity. So the capacity takes the following form. And here it is in terms of, so we just have to solve for nu star. Once we find the optimal Lagrangian multiplier, this gives us the solution. So
you just do like a search for the.
Well, I mean, you can find it. I mean, you can solve it. You don't need to do a search, but just intuitively, the way you think of it is that it's this water filling thing. But I mean, we can solve it using the KKT Conditions. But I mean, we don't know that until we actually have we can't solve it exactly until we have specific values for the noises and a specific value for P, the overall constraint. But this is the general form of the solution. So we plug in these values, and we'd solve for nu, and then we'd get an actual numerical value for this. But this is not something that you can do, like a lot of what we've done in the past is, like in the BSC, we can have this really nice simple expression for the capacities. I mean, now we're coming up with more general solutions, and oftentimes for real problems, the only way to get the solution in practice is to do numerics, is to actually run an optimization. These are complicated optimization problems, and especially in network information theory, it gets to be the point where you're really coming up with algorithms for finding a solution as opposed to actually expressing even analytically a solution. Because here, at least, we're still analytically expressing the solution in terms of a relatively small number of quantities. Do you have a question?
I was just going to ask you to analyze that paper, but you get a pretty good chance.
Yeah, answer that question. Yeah.
So, one other question I have: do they practically do, like in a wireless system, like maybe a remote system or something? Do they actually run this optimization or do something?
Well, I mean, I'm not a wireless expert, but there are today's wireless protocols, especially at the research level, are extraordinarily deep and rich and interesting, and so this capacity is still, these are one of the earlier results on network information theory, even before it was called network information theory. So, but on real wireless systems, yes, absolutely. There's no way you'd get a solution. I mean, even usually, like on real wireless systems, you only have a model of the channels. You don't have the real profile of the channels. I mean, is it really Gaussian? Is it approximately Gaussian? But yeah, you would run. I mean, constantly you're doing optimizations And cell phones are constantly doing optimizations, and control towers are doing optimizations, and Wi-Fi networks are constantly doing optimizations, and latest protocols are constantly doing computational optimizations to figure out capacities and how to send bits and measuring things and looking at feedback and reallocating bits. I mean, I'm doing that right now. I'm sending wirelessly from this iPad to this laptop, even though it shouldn't be happening since I've got a wire attached to my iPad. That's a different topic. But yes, it's like when this undergraduate connects to our laptop, it's probably saying, oh, I've gotten some bit errors. I better reallocate my bits to do something differently thanks to this undergraduate trying to connect to our. I'm assuming it's an undergraduate, by the way. I don't want to. It's an equal opportunity university. Maybe it very well could be a graduate student. Maybe it's even the dean. Who knows? Maybe the dean is like, what is that Apple TV on my network? And then not only would it be some undergraduate's girlfriend breaking up with him, but it would be like the dean saying that the chair of the mechanical engineering department's salary is not going to be raised by more than 1% or something. I don't know. It could be it's a completely different message. So, did that answer your question? Sorry. Yes, I go on tangents. Did you have a question?
Yeah, so NS can be any function of frequency, right? I mean, everything holds.
Yeah, this is
to be like a flat spectrum.
This is sort of bandwidth in specific, but you could imagine, in fact, derive a bandwidth specific version of these, and each one of them, then you have a bandwidth restriction as well. But we do have. We're going to talk about the spectral variant of this. I mean, we're going to see. In fact, I think the next slide. So this is like what we did before. Let me just go through this. I'll answer your question in 1 second. So this is in bits per transmission. So this is bits per parallel channel use, and this is bits per transmission. You take the average. Okay. But then, well, can I have a whole discussion that I think addresses your question. So we're going to talk about colored noise. We're going to talk about spectral water filling. So I think that will address your question. But at that point, maybe let's come back and make sure that answers the question. But right now, we're not really talking about the case when the noise is non-uniform. Like when there's colored noise. We're talking about pretty much white noise. Were there other questions? Okay, so the next thing we're going to do, and this is going to be important for us to analyze because what we want to do ultimately is analyze the case when there's feedback, is when there's when there's correlated noise. So uncorrelated noise means basically, again, that this matrix is diagonal, the noise profile. But thanks to the fact that we've expressed it as a joint Gaussian with a covariance matrix, we can talk about colored noise, which says, okay, well, rather than it being a diagonal covariance matrix, let's just say it's some positive definite covariance matrix, K sub Z. So that means that the noise is correlated. It means like, so remember we've got K channel uses, and the noise we're saying, this is this noise vector here. It was the case that these were independent Gaussians. Now it's just some joint Gaussian. So we sample from a joint Gaussian. If we know the noise at time step 1, that might tell us something about the noise at time step 2, which might tell us something about the noise at time step 3, and so on and so forth. But it's still jointly Gaussian, and it's also still independent. So we're not saying that the x's and the z's are correlated with each other. We're just saying that the z's are correlated within each other. So now the signal source correlation is, well, at least from the perspective of a first order measure, is defined by the correlation matrix E of XX transpose. So we can express the power constraint. Since the power constraint is going to have the same form, we can express it as a trace. It's the trace of kx less than or equal to n times p, which is this. All right, everybody agree with that?
Yeah.
Yeah. Okay, that's an easy one. Oops, I keep drawing these yellow lines. Now let's first, as we've done in the past, form an upper bound. And we've got that, everything's bounded above by a Gaussian with, thanks to the independence correlation matrix kx plus kz. That's the entropy bound. Bounded above by a Gaussian with that particular correlation matrix, Gaussian's entropy with that particular correlation matrix. And that's, again, doable because of the independence assumption. Okay. Now the noise is fixed, right? It's uncorrelated. It's correlated, but it's fixed, and so we want to maximize. We want to maximize k sub x, right? This guy here in this equation. And so here's the actual form of the optimization problem. So we want to. This looks like it's tricky, right? So we want to maximize. It's with a positive, or in this case, it's a non-negative definite constraint of the determinant of kx plus kz, subject to this power constraint. Again, this is a joint power constraint. Okay. Does that make sense? So again, we're if you're wondering, I mean, by the way, so remember we're this sort of upper bounding and then finding something that achieves the upper bound. We're sort of assuming that we can do that implicitly now. We've done that enough times to say, well, we upper bound by Gaussian, and in order to make it Gaussian, we make sure that x is Gaussian, blah, blah, blah. So then the last thing to do is say, okay, well, under the Gaussian thing, how do we maximize this upper bound? Because we assume we can achieve the upper bound by making everything Gaussian. So that's why this is valid. That's why we're, in order to achieve the capacity, we're going to turn this guy into an equality. But then to make the capacity, we turn it into a Gaussian, entirely a Gaussian problem. And the entirely Gaussian problem is equation 21.22. Positive definite constraint. Now, to solve this, we can use VD, and we can express kz using its singular values. I mean, if everything's square and positive definite, this is an eigen decomposition where we represent kz as q and a q transpose, where q's are unitary, so and orthogonal. So basically it means that the determinant of q is 1, and q transpose is the identity matrix. So it's a bunch of orthogonal vectors, unit vectors that are orthogonal. And so then we can write the objective in this fashion. Here's the objective. We express kz in this spectral way, but then we can factor out on the front a q and factor out on the back a q transpose, which turns, gets rid of, in some sense you might think this doesn't help very much, but what it does do is it isolates the problem to be one where, in some sense, we're rotating the problem with respect to the noise. And this is sort of interesting. So what we're going to do with this Q, these Qs are really rotation matrices. They're just sort of rotating everything in such a way so that this noise vector, right, this lambda is now going to be diagonal. Right? This guy here. And this guy, k of x, wasn't really necessarily diagonal, so it turns into a. The determinants, these guys go away because the determinants of those guys are 0. But now we've got, in some sense, a problem that sounds, or at least seems to be very similar from before, which is the uncorrelated noise case. But we rotated the axes along, since the noise is fixed, to an axis such that the noise is suddenly uncorrelated. And we've got this kind of form. Let's see if that's useful for something. So we have an expression for kx. Thanks to the orthogonality of the vectors, we can express kx in a variety of these different ways. So, everybody comfortable with this? Okay, so what happens? Well, since there's something called the trace trick, and the trace trick is universally useful in the context of Gaussians. And so when we're interested in something like the trace of A, or the trace of k of x, and again, thanks to the orthogonality of the Q, the trace of A is equal to the trace of, well, the definition of A. But the trace trick says, well, we can rotate these matrices. We can stick the right-hand Q over to the left-hand side. But then Q's are orthogonal. So the trace of A is equal to the same as the trace of k of x, which is our original thing we wanted the trace for. So the power constraint is the same, thankfully. Right. So we've got the non-negative definite constraint, subject to the same power constraint, because we haven't really changed the power constraint. The trace of A is equal to the same as the trace of the other thing. But wait a second, does this look similar to our problem? Well, not quite yet, because we're saying, well, this constraint is that A, we maximize over the set of non-negative definite matrices A of the determinant of A plus lambda. But now let's step back for a minute and say, well, what is it that we really want? These are going to be, this is the covariance of this jointly Gaussian random vector of random variables. Right? And when is the entropy maximized? When they're independent. Right? So we can just right away say, wait a second. If we have any jointly Gaussian, say U, here's the entropy. That's upper bounded. We know that the entropy is upper bounded by the sum of the entropies when everything's independent. And each entropy is just going to have a form which is the variance in the diagonal term. And so that's basically equal to the entropy when we just take the diagonal elements of the covariance matrix case of U. So this is really easy to do. So this determinant just turns into a product of the diagonals. So it suddenly makes this optimization problem really easy. So we have this, or in other words, this upper bound. And again, that comes from, thanks to so this is in some sense an example of an inequality, of a matrix inequality that comes very easily thanks to knowing about the entropy of a Gaussian, and that entropies are upper bounded when you take the sums of the individual entropies, which comes from the case when they're independent. So then the problem then simplifies too. I mean, it's an upper bound, but that we know that the solution is going to be here. And so we can maximize. The only constraint now is that each of the AIs, each of the diagonal entropes can't be negative, right? Because then there wouldn't be corresponding sort of variances or powers. And then the trace is just the sum of the corresponding diagonal entries. It's the same thing. So this is almost exactly the same form of solution as we saw last time. And again, I think I already answered this, but we're saying we're using the equality form again because it's never going to be the case that if any of them are strictly less, if this sum here is strictly less, we can always improve our solution by making it tight. So the solution is going to be a tight point. And I guess something else I should say in that context is that that also holds in this particular case because lambda I is non-negative. Okay, so we can sort of use the solution, the water filling like solution we did before, which basically says that AI is equal to nu minus lambda I plus. And so we get this form of the constraint. So we go through the optimization problem and we get the capacity in the following form. So it's exactly the same, it's just in the rotated dimensions. Right? So this is water filling. It's the same water filling argument, but now what we're doing is we're water filling on the eigenvalues of the noise covariance matrix rather than on the noise covariance matrix. It's the rotation along the axis where everything's independent. And we get a solution of the rotated signal powers, which are the AIIs. That doesn't mean that those are the signal powers. We need to rotate them back. So now we've got the solution A, and we recorrelate the A's with this orthogonal matrix Q to sort of bring the signal powers back to where they're sort of matched to the noise profile. So, I mean, all this basically means that we've got colored noise, rotate it to orthogonal dimensions, solve it, and then take the solutions and rotate the solutions for X back to profile of the noise. It's a very, very intuitive solution.
But it's not sparse anymore like the last one was.
Well, it might very well be sparse in the rotated dimensions. But once we rotate it back, it would be surprising if it's still sparse. But it's still sparse in the eigendimension space. Because it's still this water filling thing. But remember, we might take a sparse vector and you hit it with an orthogonal transform. It'll be sparse. Okay, so let me take a break. I mean, so the spectral noise is this next topic, but let's take a break and we'll get to this question that you had before. After the break. So I'm going to pause the video and see you after the break. So we are continuing after our crash. But I think everything up to then, I don't know why it does this, but we've not lost anything. It just crashes at the point when I restarted. So anyway, so the stationary Gaussian process case is when we actually have, in some sense, kernel functions which sort of give us the covariance matrix for both X and for the noise. And because it's a covariance, because it's a kernel function that gives us the covariance, these are sort of positive definite functions, it gives us essentially what are called Toeplitz matrices, which means that each diagonal is the same is the same values along each diagonal. So now I wasn't planning to analyze. This really gets to your point, but it turns out that when you do have these sort of spectrally non-white noise sources, what you can show is the following: like you get a power spectrum of the noise in the signal. So you need to analyze it in the frequency domain, in the spectral domain, in terms of the power spectrum. And the power spectrum essentially gives you like statistics of what's likely, how noisy it is, how powerful, or what's the noise as a function of the frequency, which is omega, and you get something which is very similar to the water filling argument, except that now you need to integrate along frequency rather than summing along channel use. And the integration along frequency gives us the capacity, but where we have a Lagrange multiplier nu minus the power spectrum of the noise. And so it's exactly the same water filling like procedure, but with respect to, rather than the noise profile of each individual channel, it's with respect to the noise profile in the spectral noise profile. And so we get a pattern which is kind of like this. If we were to integrate from, if it's discrete time, then we'd integrate from 0 to pi, we get that the water filling would be exactly analogous, but now what we're doing is doing it in frequency domain. I know I'm not doing this topic justice, but the analysis is very similar, except that one needs to worry about the integrals rather than the sums. But other than that, it's quite similar, and you have to do it in the spectral domain. So what this means is that when one controls the signal power, one needs to put signal energy where the noise power spectrum is low, and you put no signal energy in these regions where the noise power is high. So you need to band limit or comb limit in some sense your signal power, signal energy. But as your overall joint power constraint increases, again, you start adding more and more signal energy to these regions where there's more and more noise and energy. Okay. So does that answer your question? I mean, without actually answering your questions, maybe it sort of gives you the idea. Like I said, I wasn't planning to analyze it. What I wanted to do is talk a bit about feedback. Because we talked about the case when we had feedback in the discrete memories in this case, and we found that in the discrete memory in this case, feedback doesn't help. Because in some sense, when we're coding at the channel capacity limit, if you recall from last quarter, when you're coding at the channel capacity limit, you sort of in some sense already know everything about the channel, and memory doesn't tell you anything. And so feedback is telling you stuff that you already have taken account of by the fact that you're coding at the capacity. Although it can make encoding and decoding easier, it doesn't actually increase the number of bits per channel you can use. But it turns out that now, in this correlated Gaussian noise case, we actually have a very, very nice and easy way to represent a form of a non-memoryless condition. So we said last quarter that if there was memory, in other words, if let's say the noise profile goes up and down at some rate or something, and if we find out, oh, we're getting to this region where the noise is getting really, really bad, the feedback would tell us that. We'd say, wow, we sent this and we got that. God, I can't believe you got that. This is what I said, and that's what you got. And that's something that we could use to maybe change our encoding strategy. Now, in the Gaussian case, when we have correlated Gaussian noise, that's a form of non-memoryless, right? Because we've got a bunch of these channels with correlated Gaussian noise. What does that mean? If the Gaussian channels are being used successively in time, it means it's not memoryless, right? It's a form of non-memorylessness. Or, if you prefer a less polysyllabic description of the word non-memorylessness, you could just call it memory. Or for those of you who prefer very polysyllabic words, just go ahead and keep calling it non-memorylessness, which is not a word at all, but it is on the slide, so I have to say it. Non-memorylessness. Now, the other thing to note is, and what's distinct about this scenario, is it's no longer the case, like we analyzed previously, that we can assume that the x's and the z's are independent. And the reason why is because we're going to be using the feedback to change our encoding strategy. So the z's, as the z's are, the z's are going to be something that's going to be affecting our x's. We're going to get y. We're going to get some kind of feedback. And it's going to say, oh, you got that. Well, then therefore I'm going to do this. So that means that the z's and the x's now kind of influence each other. Or there's some sort of dependence. Because the next x's that go out might be different depending on what the previous z's were. And the noise is correlated, so we can use the previous received. I've already said this. We can use the previous received values to help predict the noise. So here's our encoder, or the definition of a code. So it's really a set of mappings. So it's a 2NRN code, which is a set of mappings of the following form. So we have a message, omega, which is again one of an integer from 1 to 2 to the NR. And N is our current rate. And we have a vector of real numbers, which are the messages that were received. And so, again, with feedback, we're assuming that we've got perfect feedback. You can think of it as a coding function rather than just sort of a set of code words. And we still have a power constraint. This is our power constraint. And in fact, this is not only for all W, I should say, but also for all Y1 to I minus 1. So you always have to satisfy the power constraint. Now, when we had colored noise without feedback, this was our capacity. And so this is the thing we're comparing against without feedback. And we want to see, in some sense, how much better the feedback case is than the non-feedback case. And I have to sort of forewarn you that we're really not going to get to this goal really until the end of the matrix inequalities section. And you might think, well, why? Wait, so matrix inequalities, we're going to say, by the way, you can do all these great matrix inequalities, and then at the end of that section of the lecture, which probably at this point we're not going to get until Wednesday, we're going to come back and finally compare these things, namely this guy and this guy. So don't adjust your expectations once we've switched to matrix inequalities away from capacity with feedback, because we will be revisiting capacity with feedback once we can utilize these fantastic, amazing, incredible, juicy matrix inequalities. Okay. Now, you might think, well, why might we want feedback? Does anyone have any ideas why feedback would be useful?
We have to assume that feedback is perfect, right?
I think for this model, for the analysis, we're going to assume that. Now, obviously, in real life, it's not perfect. But there are situations where feedback is such that, the capacity of the feedback channel is so much greater than the capacity of the sending channel that it's not so off to make that assumption. So where are some instances of that where that might be the case? There's one I thought of, which I think is a great one. But I wanted to give you guys the opportunity. I mean, of course, I thought of it, so I think it's a great one. But I mean, I think it's very timely. I'll give you an example. So the Mars rover, right? So you're this, Mini Cooper-sized car which is driving around on Mars, which is, quite far away, I think. And you have limited energy and limited battery resources and limited communication, limited ability to decide things for yourself. Even just spending energy deciding things for yourself might drain your battery and you might be stranded there. Whereas here on Earth, we have plentiful energy and we can focus lots and lots of antennas on this one point on Mars and everything. So we can send stuff to Mars rover pretty reliably, right? We can send a very, very strong signal. This thing out there has got to be very, very careful about sending information back to us. It needs to be useful and it can't be spending too much energy. computations that it does. So that's sort of an example. But there are other examples as well where you might have asymmetric communication. Anyone have any ideas? RFID? Do we ever send anything to RFID tags? I thought that's unidirectional.
The tags can backscatter.
So, well, how is it that you send it something? I mean, you sort of send it. I guess you're sending it really just something to sort of end up reflecting in some sense back to you. But you're not really sending it. So you do send it commands to do different things.
Queries.
Yeah. Okay. That's a good example. Although these things are passive as well, so they're the energy is essentially coming from you, not from it. And it's not going to change its coding strategy depending on whether or not you've received the message correctly or not.
And what if you had something where you're trying to minimize your chance of being detected that you were communicating? So you had that as an additional, if you're trying to optimize your capacity, but also with some kind of constraint.
Okay, so you're trying to talk to me, but you don't want anybody to know
Yeah,
what you're saying.
I have a bug in your office or whatever, and you have sensors to pick up on it.
I see. So, and I'm telling you, I got this, I got that, and you're very, very cautious about. And you're doing that right now too, right?
Nobody's in your office right now.
That's right. Okay. So no, that's a good example. There are a couple of other ones. Some sensor networks are like that. I mean, low power sensors. RFID is a good example, but I think that there are other sensors that actually aren't entirely passive. Like some people are working on. People in our department are working on like building, wallpaper with built-in sensors. And these things start with power, but maybe the power lasts 15 years. And most people change their wallpaper every 15 years anyway. Is this a wallpaper that people use anymore? But anyway, wallpaper, which maybe you might have lots of sensors, and these things have like tiny batteries which might last for a long time. But then you have to be very careful. You can communicate to them, but they have to be very careful about communicating to you. And it's a big deal to sort of rip out your walls and replace these things. Or internet service providers, Comcast. I mean, it's not as extreme an example, but you have bidirectional. Download speed is usually much greater than upload speed. And to get to the other question, you can think of the feedback being partially noisy, but it's really the issue is the asymmetries exist. So let's use a graphical model to describe it. So before we have, in some sense, a graphical model to describe feedback without correlated noise. Without feedback and without correlated noise. So we have all of these sort of, in some sense, separated Gaussian channels, where let's just zoom in on it. This is one of these fantastic pictures. So we have Y is what's received, X is what's sent. Y is received, X is sent, and Z is the noise. And we have all of these things together. So Y is received, X is sent, and Z is the noise. And Y is sort of additive. It's X plus Z. Okay. When there's correlated noise, you can construct a Cholesky decomposition of the covariance matrix of the Gaussian to obtain a directed graphical model description of the Gaussian, which represents exactly, or is represented exactly by this picture here, which basically says, okay, well, first you choose Z. Let's zoom in a little bit on this, if we can see this. First you choose Z. And then X is what you want to send, and then you get Y, which is the sum of X1 and Z1. Then Z2 depends, the noise, Z is a conditional Gaussian, which depends on Z1. X2 is what you want to send for the next Gaussian channel. You get Y2 is equal to Z2 plus X2. And then Z3, which is now conditional Gaussian on Z1 and Z2. And this continues, and it's not until the very last element of this vector, Zn is a conditional Gaussian dependent on all of Z1 through Zn minus 1. And that's sufficient to describe a joint Gaussian, even though there's this sort of ordering associated with it. And any ordering works. In fact, you can do a decomposition for any order. But any ordering works. And so that basically corresponds to the correlated noise case. And the ordering that you choose is the one of time. Now, what feedback says, so, remember, so in the independent case, none of this, like correlated noise, now it makes a lot of sense that this means that there's memory, right? Because when we order this in terms of time, the z's are now dependent on each other in terms of time, right? And so now feedback basically says that, okay, so here's our noise guy. Here's what we want to send, and we get y. Okay. So now Z2 is the noise at time 2, which is conditional Gaussian dependent on y on Z1. And then X2 is what I want to send, but X2 gets to use Y1, which was the thing that was received. And the idea is that this connection here, let's draw it in green or something. This green connection is, presumably perfect. And similarly, X3 gets to use both Y1 and Y2, and X4 gets to use all previous things that are received. And they're all a function of W, which is the message. Right? So the message is what we want to send. Right? But does this picture kind of make sense? This is our model. This is at least a pictorial, graphical picture of our model. So then we have that the noise, since y is equal to x plus z, that gives us that z is equal to y minus x, which means that when we want to compute the mutual information, we represent as the difference of entropies, we get the same kind of thing we saw before, which is that, well, Z is still a Gaussian, it's a joint Gaussian, and it's a correlated Gaussian. And then this thing here is still max when it's a Gaussian, just like what we saw before. So max then is achieved when X is also Gaussian. And it's jointly Gaussian, which I think this is, it's not such a hard exercise to show. But I think we can believe this at this point in this class. Now, the other thing to note is that, we don't really need to know, thanks to this joint Gaussian aspect of things, we don't really need to know the previous value x if we know the previous value y. So in other words, to make this more precise, when we're saying, okay, well, x is a function of the w and the previous y's, which, we can always say, well, it's a function of the x's and the previous y's, and it's also, so therefore it's just a function really of the z's, thanks to the joint Gaussian. And there's also a w in there that's missing. Obviously, you need to know the message to send it. So, so again, thanks to the joint Gaussian, the x is really just a function of the noise and the message. And so therefore, all the x's can be written in this fashion. It's a conditional Gaussian conditioned on the noises, where there's sort of a residual of this form. So xi is equal to the sum for j is equal to 1 to I minus 1 of bij zj, where zj is the jth noise, plus some innovation, vi, where vi is some other Gaussian, which is independent of the previous j's. Okay. Now, if you're wondering where that follows from, well, let me just write down the expression in general, vector expression. The vector expression says that the n x's is equal to B, Z plus V, where B is a strictly lower diagonal matrix that has zeros along the diagonal. And the reason why it has zeros along the diagonal is, again, because in this expression, we're only going up to I minus 1 here. Okay, so we're not using the ith z. Here's a sort of general result that shows you this. So this is, again, the Cholesky UDU style factorization of the covariance matrix of Gaussian. So if S is a joint Gaussian covariance matrix K, then you can always write SIs in this form. Where the B's come from? So the B's, the Bij's come from the Cholesky decomposition of the covariance matrix, where U is an upper triangular matrix with ones along the diagonal, and then you get rid of the ones by just saying B plus I. So B is one of these upper triangular matrices with zeros along the diagonal. And then D is just a diagonal matrix of condition variances. This is a and there's one of these undergraduates again. So this is the standard result in Gaussian theory. Yep.
So you're saying S is a multivariate Gaussian, and the S sub I is the different dimensions of that multivariate.
That's right.
Gaussian random variable.
That's right. Exactly. Okay. So now B is what controls the feedback, right? So B is essentially where we're getting the information from the previously received signal via what we're doing, and we're representing in this form, again, thanks to the joint Gaussian case in terms of the noise. So if all of the B's were 0, then we'd have no feedback at all. So it's the general conditional Gaussian. And so we actually have this form of optimization problem. We can write it in this way. So here's the capacity with feedback. So we still have this trace power constraint. That hasn't changed, because those are the individual powers of the sums of the powers, right? And then we have this form of the objective, just like what we had before. This is the signal, sort of a form of the signal-noise ratio. But then we can write it in this following way. We can write it as the max over this non-negative definite constraint and this predicate on the matrix B being true. So this is the predicate here. And I'm going to derive this. This looks fairly complicated, but I'll derive it in the next slide. And then the objective becomes this whole thing. And that will also be derived on the next slide. Now, you might think, just before you saying, well, these are complicated, these are getting complicated expressions. And you're going to see that where the matrix inequalities are going to come in is going to allow us, once we've derived this expression for equation 21.48, we're going to be able to look at and compare the capacity with feedback and the capacity without feedback and see how much bigger they are. But it's more a fairly algebraic derivation of equation 21.49. And a lot of this stuff, I'm going to go through it quickly, but I think this is probably best to do offline if it's not entirely clear, but I think it's not so bad actually. So the thing to realize is that when x is equal to bz plus v, and thanks to the independence equation, we can just look at the covariance matrix of x, and then we write this in this form. Then this form here is just equal to that, and that gives us, so b kz b transpose plus kv corresponds exactly to this down here. Trace of b kz b transpose plus kv. Okay, and that follows from this form here. The other thing that happens is when we look at this. So here's now we're doing this objective here. Okay. So we want to look at the covariance matrix of x plus z, which is exactly equal to this guy. And we expand it out by looking at its definition to give us this one. It's bz plus z, so that's the same as b plus iz plus v. And it's just the same thing on the other side, but there's inside of the transpose. Then we can suddenly write it in this form, where we've got zz transpose in the middle. And we've got this term, and then we've got the VV transpose. But thanks to the independence property, this stuff cancels out and this stuff cancels out. And so what we're left with is this plus this. So hopefully we'll remember that b plus ikz, b plus I transpose plus kv corresponds exactly to what lies in the numerator up here. B plus ikz, b plus I transpose plus kv. Not so bad. Okay. So then, this is the expression for the capacity. Now we don't yet have the tools to compare this to the non-feedback case. But what we do have the tools to do is to prove that this is really the capacity. Because remember, this is the information capacity. This is the result of the optimization problem. And what we need is a theorem of the following form. In fact, we need the following theorem, which says basically if you've got a Gaussian channel with feedback in the fashion that we've set it up, and hopefully that, at least the fashion that we've set up the setting is clear, that and this is a statement, this is a theorem whose statement is very similar to the theorems that we've already seen. For any sequence of 2 to the n or n codes with probability of error going to 0 as n goes to infinity, the rate has to satisfy this inequality. Right? So the rate can't exceed this feedback capacity as the block length gets big. And vice versa, there's a converse to this theorem as well. But let me just make sure, first of all, that everybody understands the theorem. There's exactly the same form of the theorem. It's saying that it's a Shannon form of the theorem. This is another example of how Shannon came up with this sort of paradigm, which became sort of the model with which people define capacity for sorts of these kinds of things for many, many years, and in some sense today still. This is over 60 years old. The paradigm of saying that there's this point, this critical point, that as long as your rate doesn't exceed it, and if your block length gets big, you can communicate with effectively error-free. And if you do exceed it, you'll get errors. If you don't exceed it, you won't get errors. And here is just saying, okay, well, it's the capacity of the feedback case. Now, I was going to go through the proof, but maybe it's not that enlightening. It's just more algebra. Well, it's not really algebra, it's information theoretic algebra, which I think we've already done enough times last quarter. So, and then there's also the converse of the proof, which I wasn't going to go through. But let me just make sure that the statement of the theorem is clear. Is everybody happy with it? What it means? So it's very, if you even to understand our very, very first capacity theorem, this should be clear. This is the form of perfect communication that we've got. Namely, there's this critical point. And that critical point is the result of that optimization problem. Okay, so but what we want to do is go to this matrix inequality section. And so we are going to get to that today, which is good, because that means we can get a good start on rate distortion theory on Wednesday. We're going to prove a number of useful matrix inequality theorems, and then along the way visit this comparison of the feedback capacity in the Gaussian case with non-memorylessness and the non-feedback case. So everybody sort of get where we're going? the idea? Speaking. Okay. All right, so a lot of this material is drawn from chapter 17 of the book. So chapter 17 is sort of like a mix, a mishmash of different, is that right? A mishmash of different inequalities. Is that a correct technical description of chapter 17? Mishmash? Or is it mashmish? I don't know. I think it's funny. Okay, so here's our first inequality. This is a really easy one. Basically, it says that when we've got a bunch of d-dimensional random variables whose we've got a covariance matrix, which isn't necessarily, it's not necessarily a Gaussian, this is just properties of covariance matrix. It's basically saying that k of x plus z plus k of x minus z is equal to 2 of kx plus 2 of kz. And the way we get that is just by using expected values. This is very simple. K of x plus z is equal to this. I'm not saying anything about them being independent, so nothing cancels out. That's k of x plus z. This is k of x minus z. It's equal to that. Sum them up, and get this and this, and this and this survive, and this stuff and this stuff cancel out. Okay, next. First matrix inequality. That one we didn't use any information theory, so that's sort of just an extra one we need. The second one says, okay, if A is non-negative definite and B is non-negative definite and A minus B is non-negative definite, then the determinant of A is no less than the determinant of B. Sorry. Hold on a second. Why is my laptop ringing when my phone rings? Yeah, that's right. So here, all right. I've connected my cell phone to my laptop. So now when I'm in the middle of lecture and my cell phone rings, my laptop rings. So that's what's happening. And it's now eternalized on YouTube for the rest of human history. So, I'm saying, it's like hundreds of thousands of years from now, ancient archaeologists will be poring over these YouTube lectures and will find this telephone call. These so primitive, stone spears and Google Hangout. That was what they had. Okay, so anyway, let's go through this guy. So A is we already said this. So basically, let's C is equal to A minus B. Okay, defining a new matrix, and assume that X is since everything is non-negative definite, we can define Gaussians. And since we can define Gaussians, we can use the entropy of the Gaussian. This is where we're going to get these inequalities from. So, what's cool about this? I think this, if this wasn't clear, hopefully this is clear. This theorem has nothing to do with information theory. It just has to do with, it's a matrix inequality. But we're going to use entropy to prove it, or Gaussian entropy in particular. So x1 is normal with a covariance matrix B. X2 is normal with covariance matrix C. And this makes sense. Why? Because A minus B is non-negative definite. So this guy isn't an invalid thing to do. And let's also assume that x1 is independent of x2. Okay? So then y, let's define y to be equal to x1 and plus x2. And so thanks to the independence of x1 and x2, y is normal with covariance matrix B plus C, but B plus C is equal to A, so it's normal with covariance matrix A, which again makes sense because A is non-negative definite. Okay. So using the properties of conditional entropy, we've got the entropy of Y is greater than or equal to the entropy of Y given x2, but once we've got x2, the only residual uncertainty is x1, so that's equal to the entropy of x1 given x2. But since they're independent, it's equal to the entropy of x1. So we've got the entropy of y is greater than or equal to the entropy of x1. And the entropy of y is equal to 1/2 log 2 pi e to the n determinant of A. Well, it's log. We'll put a log in there. It's greater than entropy of x1, and x1 is got this entropy. And so we just get rid of all of the common terms, and what we're left with is this part up here.
That's pretty cool.
It's amazing. Yeah, it's absolutely amazing that from Gaussian, I mean, what is the critical property that we used? Conditioning reduces entropy. So oftentimes, and I mean, for those of you who are interested in submodular functions, like for example, proving that the log determinant is submodular is extraordinarily difficult if you just do it without the information theoretic proof. So like I've seen proofs of it that are pages and pages, but then when you use an information theoretic proof, it's just a one-liner.
And you also need that every positive definite matrix, the covariance.
Yeah, but that's a standard result. It's from Gaussian theory. I mean, here I'm doing it for non-negative definite matrices, and it's a little bit easier to do it for strictly positive definite ones, but you can always define, I mean, you can sort of find a weird Gaussian on a lower dimensional subspace, and if you then project onto that subspace, then it becomes positive definite again, as long as it's not 0. But then it's just a point. But it's okay. It's still relatively kosher to say it's non-negative definite, which is what we're doing there. And the result holds for non-negative definite matrices. Okay, the next one, this is going to be the last one, is, again, x and z are arbitrary. Then we can bound the covariance matrix of the sum of x and z by 2 to the n, which is the dimensionality, n is the dimensionality of the random variables, 2 to the n of the determinant of the sums of the matrices. Okay. So how do we do this? Well, we take, remember this inequality? That was from a while ago. And so that basically means that this guy here is equal to this, which is non-negative definite because it's a covariance matrix. There's the bell, which implies this. And so when we take the determinant of both sides, we've got this. And there's a fact about the determinants where the determinant is, let's say, equal to 2 to the n of if you put a constant inside of a determinant, you bring it out by raising it to the dimensionality of the matrices that you're taking the determinant of. And that's where you get the result. So anyway, so we'll finish with this on Wednesday. Are there any last questions?
Does that assume x and z are independent, or
We're not assuming x and z are independent.
so it's any?
And we're not even necessarily assuming them Gaussian. I mean, because remember, this has nothing to do with Gaussian. It's just a matrix inequality. Okay, so let us now pause or stop. And this is probably going to crash now.